Okay, so I just wanted to do a walkthrough of the solutions to the 12-week review problem, so that way if you're not able to make it to the group EI on Thursday night, that you have some way to hear a little more about what these problems, what the solutions are, and how I solve these problems. So to start off with number one here, how would you clear the interrupt flag for an interrupt on EINT2? So external interrupts, this is just from the notes. You write a bit, a 1 to the bit of the external interrupt that you want to clear. So for EINT2, that's bit 2, and that is in extint. For part B, how would you clear the interrupt flag for the SysTick timer interrupt? That is reading ST or CTRL, again, just from the notes. This is how SysTick works, so when we read from that register, that's what triggers the flag clear in the hardware. How would you clear the interrupt flag for PWM1 interrupt? This is roughly the same as external interrupts are. We write a 1 to the bit for which interrupt we're working with. So if it's MR0, the period timer, we're going to write a bit to bit 0, or write a 1 to bit 0. If it's MR1, we're going to write a 1 to bit 1. And that's, again, just defined in the manual. We can look those up. How would you clear the interrupt flag for the ADC interrupt? Again, from the manual, we read from the data register. So you remember if you did the lab 7, when you read from 80DR2 to get the 80.2 value, that clears the flag. You don't have to do anything else special. And it's nice because we're already reading from that to get the value anyway, so it just kind of works out that it clears it at the same time. Why do we need to clear the interrupt flag? Well, clearing the interrupt flag prevents duplicate interrupts. So that flag is set to indicate to the hardware that it should call the interrupt handler, and whenever that flag is set, it's going to continually do that. So if we don't clear the interrupt flag, it's going to call the interrupt handler again with the same stuff that we just handled, and that's going to be a problem. So we want to make sure we clear that interrupt flag every time. So that's it for question one, just some trivia about the external interrupts and interrupts in general. The really important thing is that we do want to clear the interrupt flags every time. On to problem two. So this is dealing with assembly in C, which we transitioned over the over this part of the semester. And what this question is asking is to translate the code below into Thumb2 assembly. So we're given some C code. We're asked to translate that into assembly code. So let's just walk through what we're seeing here. The way I did this was just walking through the code line by line, going from the top of the C code and translating to the assembly idiom for that thing. So an unsigned int foo in C with 2 parameters is just a sub procedure in assembly. So it's just foo proc. And then the end p, so the foo proc is the beginning of this. That's the unsigned int foo, unsigned int x, unsigned int y. Same thing, is just foo proc. I do have a comment here to show that R0 would be the thing to hold X, R1 is the thing to hold Y. So that's coming from our definition of how registers are used in the Thumb2 architecture, in the ARM architecture. And that is that R0 through R3 hold the parameters in that order. So just going across the page, we would have from left to right R0, R1, R2, R3. Anything else gets put on the stack, but I'm probably not going to make you do that. So that's what our function definition looks like. The end of the function, this end curly brace, is the same as the end p here. We then look at the code that's in this. We're doing x equals x plus y. So if we assume that R0 is x, we're adding to x the value in y. And this add is, R0 equals R0 plus R1. We have nothing else there but to return x. So returning happens as though, whatever value is in R0 is our return value. And so because we already have x in R0, we don't actually have to do anything here. We can just BXLR, which is the same as returning. We're returning x just by having that value in R0 already. So that's it for foo. We'll move on to the main procedure, which is underscore underscore main in assembly, and then proc. We initialize a volatile unsigned int pointer called mem, and that's pointing to 10002000. In assembly, we're just putting that value into a register, so I chose to use R2 and did a move W and then a move T. So move W sets the bottom the bottom 2 bytes to those values. Move T sets the top byte to those values, or top bytes to those values. So we're just setting 10002000 in a register, and that's equivalent to the volatile unsigned int. And then we have the line star mem equals foo star mem 2. So this is quite a sort of mouthful, but what we're doing here is we're calling foo with the parameters mem dereferenced and 2, and we're putting the return value into the address or into the memory at mem. So we first load into R0 the value at address R2. So that's getting the value from memory in mem, so that's basically the star mem here, and putting it into R0, which is where we expect the first argument to foo to be. And so that's just in one fell swoop. It's loading the value from mem, it's dereferencing that pointer, and it's putting it into the first place for the argument. We're then moving into R12, so that's the second argument. That's where y is going to be. And we're putting 2 into that because, again, that's the parameter that we're passing in. We then BL to foo, so that's how we call a function, is we branch and link to that function, and that allows the BXLR to take us back to the next line of code when we're done. So we jump to foo, and then when we get back, we're assuming that the return value from foo is in R0. We're going to store that into mem because we did star mem equals the return value of foo is what that line of code says, right? And so we're going to store R0 into R2. Then we're going to move R0, 0, and BXLR, and that's the return 0 part. So again, we're assuming that the return value is in R0, so if we're returning 0, we have to have that in R0, and the BXLR is what does the return itself. Then we have our end P. So that's it for that one. It's really just, line by line, thinking of what does this C code look like in assembly language, and doing that one-to-one translation. On to problem 3, which is on external interrupts. So given the state below, describe what would happen for each of the external interrupts. Assume that there might be errors in the configuration if some values, but not all, are set for an external interrupt. So this is really just going back to some of what you've been doing for Lab 5, which is trying to debug external interrupts when they don't work. So we should know by now that we set these 4 things, which are pincell4, xmode, xpolar, and iser0, to enable an external interrupt, and we have to set those to the correct values. So this is really just checking over, can you understand what those values mean? So for pincell4, we can pull up what pincell4 looks like in the manual here. So pincell4, let's go to that. Let's click on it. And we can see that we're going to be dealing with, as again, many of you are too well aware of, bits 20 to 21 for EINT0, bits 22 to 23 for EINT1, bits 24 to 25 for EINT2, bits 26 to 27 for EINT3. And all of them need to be set to function when 0, 1 if we are going to use them for that. So we can basically count from 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. And that's going to tell us what these bits mean. So 0, 1 for 2120 means that is EINT0. 0, 1 for 2322 means that is EINT1. 0, 0 means that this is GPIO 2.12 still. And this is GPIO 2.13. So if we go back to the manual, for pin 2.12, bits 24 and 25, if it's 0, 0, that means it is still just a general purpose I/O port. So we could set FIO dir, we could set FIO pin, and that would be functioning the way that we would expect it to as a GPIO pin. If we want it to be an external interrupt, we had to set it to 0, 1, which we did not do here. So this is sort of the first error that we might have, is that if we were trying to use either of those external interrupts, we have not initialized those values. Let's move on to xmode. Xmode, these bits are, for bit 0, that corresponds to EINT0, bit 1 corresponds to EINT1, bit 2 corresponds to EINT2, bit 3 corresponds to EINT3. And mode is going to mean edge or level sensitive. So a 1 means edge sensitive, a 0 means level sensitive. So we know that EINT0 is edge sensitive, EINT1 is level sensitive, EINT2 is edge sensitive, EINT3 is level sensitive, if it's initialized. Moving on to xpolar, that's going to tell us something depending on what what X mode was set to for that particular pin, for that particular external interrupt. So bit 0 is a 0. Combined with X mode, that means that EINT0 is edge sensitive and it is falling edge sensitive. X mode for EINT1 was 0, and this is a 1, so that means it's level sensitive. Polar means it is high level sensitive, so it is active whenever it is active high. And then for EINT2, that is 1 and 1, so that is edge sensitive and it is rising edge sensitive. And then lastly, for 3, it's 0 and 0. That means it is level sensitive and it would be low active. Finally, let's look at ICER 0. So ICER 0, we're looking at bits 18, 19, 20, and 21, and that corresponds to EINT 0, 1, 2, and 3. So ICER 0 is set for EINT 0. It is not set for EINT 1. It is set for EINT 2. So that means that we've initialized things for those ones. It is not set for EINT 3. So 0 and 3 are not, or 1 and 3 are not initialized in ICER 0 properly. 0 and 2 are. So now we can describe what happens for each of those external interrupts. Again, we've just talked through them. So EINT 0 is initialized properly in PinCell. It is set to trigger on falling edges. And it is initialized in ICER 0, so it will trigger interrupts on P2.10 on falling edges. EINT 1 is initialized in PinCell 4. It is not initialized in ICER 0, so that's going to be a problem. It's not actually going to trigger those interrupts, but that's probably good because it's set to level sensitive and it's high active. So it may actually just trigger interrupts constantly if we did have ICER 0 set. Though maybe that's what we want, or maybe this is something that's pulled to ground and is an error condition when it is high active. EINT 2 would trigger on rising edges, but PinCell 4 is not set, so it is a GPIO pin. It is set in ICER 0, so you could maybe presume that this is a mistake and that we just didn't set PinCell 4 properly. In EINT 3, we didn't initialize this. We didn't initialize either of these. We didn't initialize this, so we can probably assume that EINT 3 is just not being used here. Okay, on to problem 4. So problem 4 is an encoding problem. This is a particularly difficult one. If you've been to review sessions with me before, you know that I generally like to sort of give you a harder problem than I would likely give you on the exam and maybe trick you into learning something here. So this is having you deal with conditional execution, which we have not looked at encodings for before. And so I gave you some encodings to look through for this particular problem, which are A6-8, A6-78, A6-64, and A6-22. But I'll walk you through here. I'm not going to sort of leaf back and through between the manual, but you're welcome to do that and sort of stop the video to inspect what the ARM v7 manual looks like as I sort of talk through this. So the first instruction that we've got to encode is the CMP R0R1. Luckily, that's a pretty easy one. We're just looking at A664, which is the encoding for CMP. And if we look at encoding T1, that has the two registers that have to be 3 bits, so we can actually only encode up to R7 in these two registers. But because we're using R0 and R1, this is a nice compression technique where we can use the small numbered registers, which are a little more common, right? Because those are the R0 through R3 are the parameter registers. It's the return value for R0. They're the caller saved registers, so they're the ones that we're going to use the most frequently anyways. And that gives us a little bit of flexibility to use up to R7 as well, though we could probably even compress this to just 2 bits and get a lot of the benefit out of it. But regardless, we have 3 bits to encode our registers here. RM was the register that is in this position. Rn is the register that's in this position, and so we're just encoding 0 and 1 into those 3 bits. And that gives us our encoding, which is 4288. The rest of these bits are fixed by the instruction encoding T1. So we're just writing out those bits and then encoding R1 and R0 into that. Next, we have 2 conditional instructions. So this is the very tricky part of this problem, and that's coming from the IT block, which is defined on A6-78. So I'd recommend pausing here for a second, looking at that instruction encoding, and trying to understand what happens here, and then I'll walk through it. So the way that an IT block works is we can have up to 4 instructions in a row that use the same conditions or some inverse of the conditions. And so it gives us a bunch of sort of fancy encodings through this mask that is defined in the instruction, and then a first condition that is defined by the condition codes. So we can see here that what we're encoding is add EQ and then add NE. So EQ is equality, NE is not equality. And so because, and this was designed this way, that we have sort of one instruction that is the condition itself, and then a second instruction that is the opposite of that condition. So we can encode this into a single check or a single IT block. And so the IT block is going to basically define that we are going into conditional execution based on some conditions that are set in the NZCV bits. So this is where we have to refer to table A6-8. You'll notice that the IT block is basically, these bits are set, defined, predefined. That is always the bits that are set for an IT block. And then we have the first condition that we're going to see. That's coming from the EQ. So we have to know that first cond is EQ. That's the first conditional instruction that we're doing here. And so if EQ is in table A6-8, it's defined as 0000. So those 4 bits for first cond are 0000. The mask part is the hard part. So there we have to look at the table and see that basically what we encode is the first condition. So if we just had a single conditional instruction, we would have the IT block where we define the first condition, and then the mask would specify that we don't have any other additional conditional executed instructions. It's just the one. And so first cond defines the first one. The second one is called X here. And we look at X as either a T or an E, basically, is what this encodes. So T would mean that we had 2 things that were EQ in a row. So if we did add EQ, X would have been a T, and that would mean then, meaning that we are using the same condition as first cond. And that's what we would encode into mask. So again, you should pause here for a second, look at A6-78, and see the second table that they have there, which encodes these T and E conditions that can be the second, third, and fourth instructions that we have. And we'd see that X in this case is E for else, because we're doing not equal as our second condition. So we look in the table and we find the XYZ pair that is E for the X condition and then nothing for Y and Z, because we don't have further instructions that use this conditional execution block. And so we set X to be E, and we see that what that means is that NE is the inverse of that, and mask is defined then to be a 1 and then not of first cond. So the 1 first is just hard-coded for the mask. The second one is the inverse of first cond, and that because first cond is all zeros, the inverse is going to be a 1, and then it's 0, 0 hard-coded as well. So that's where we get the OXBFDC for this IT block. That's all that happens there. Lastly, we're doing an add, and I said to use A6-22. We're looking at the encoding for inside of an IT block, because these are both inside of IT blocks now. And so we find encoding T2 is the one that matches those conditions. This is an add using a single register and an 8-bit immediate. And it is conditional, yes, but we've encoded the conditional part with the IT block that we did before. So the IT block encoded the EQ and the NE. The add itself is just doing a plain old add. And the conditional execution engine is handling the IT block for us. So now we're just encoding the register. It's register 2 for both of those, so 010 for 2. And then M8 is just the immediate that we're passing in, which is 1 or 2. And that gives us 3201 and then 3202. So the first couple bits are hard-coded, the second few are the register, and then the last 8 are the immediate that we're passing in. So I know that's a complicated problem. Again, this is trying to trick you into learning something about conditional execution and how that gets encoded. And then giving you something a little trickier. I will try to find something easier for the actual exam. So let's move on to decoding. Decoding should be fairly familiar to you at this point. This is your choose your own adventure, where you start at page 108 in the ARM manual and you work your way through the bits. So again, I will give you on the exam the binary for the hex encoding, so you don't have to do that yourself. In this case, I'm making this extra hard by giving you a full 64 bits of stuff. So that could be 4 16-bit instructions. It could be 2 32-bit instructions. It could be some mix otherwise of those sizes. So we start on page 108. We look at the first 5 bits. It is not one of the 32-bit patterns, so we know that this first 16 bits is a 16-bit instruction. We click on the 16-bit link. The next thing we have to decode is the opcode. So we find that the opcode is the first 6 bits. That leads us to miscellaneous 16-bit instructions. From there, we check the opcode again. This is now 0100, 011. And I think that comes from 01000011 there. The first 4 bits at that point are hard-coded, and that takes us to push multiple. At that point, we're at the encoding. So we just look at the encoding and see that this is, an M bit and then a register list. And the M bit is 0. The register list is set for, basically each bit of this indicates a register number. So bit 2 being set means R2. Bit 5 and 6 being set means R5 and R6. And so we are pushing R2, R5, and R6 in the push multiple. So that's the first 16 bits. Now we move on to the next 16 bits and see what's there. We look at 11111, and we actually see that that is a 32-bit instruction. So our 32-bit instruction starts from bit 15 on the top here, and is going to go from bit 31 to bit 16 on the bottom here. So it's actually, the next 32 bits, and it is split across the lines here, unfortunately, but that's okay. We go to the 32-bit instruction encodings, and 111 is always hard-coded here. Op1 is going to be 11. Op2 is going to be 01010001. And then op is going to be this bit 31 here, because that is, if we put these next to each other, it would be 31 down to 15. But regardless, we're just looking at that particular bit for op, and that leads us to data processing register. I think in this case, op1 was important. We had to sort of highlight those bits in the manual. It's a good idea to sort of follow along, do this on a second screen or in the background. And then op2, we had to read some of these bits to lead us to data processing register. We click on that link. That takes us to the next page. We have to figure out what op1 and op2 are, and when we decode those, that should lead us to miscellaneous operations. Once we are at miscellaneous operations, we figure out op1 and op2 again, and that leads us to rbit. Rbit has sort of a funny encoding where, because we're not really encoding all that much, it's a lot of opcode to get there. So we have a lot of hard-coded bits, and then we have RM, RD, and then RM again. And if you look through the sort of instruction semantics, you'll see that RM has to match in these two places. Otherwise, it's a failed instruction. So this is, I think, just using the extra bits to double check that you encoded the instruction correctly, that there's not something weird happening there. And so we're going to double encode 5 into RM, and we're going to double it, have the single encoding for RD. So we can double check that those are the same. They are in this case, and that is what we see then is that R bit R6, R5 is the instruction. Finally, on to the last 16 bits. Now at this point we know either I played a very mean trick and gave you, half of a 32-bit instruction, and you could maybe say, like, I don't have enough bits to decode there, but really you should understand that I'm not going to do that on an exam, and that if there are 16 bits left, it's probably a 16-bit instruction. You can verify by seeing that 11100 is not one of the 32-bit encodings, and therefore it's a 16-bit one. We find the opcode, which leads us to unconditional branch, and we're actually done very quickly here. Unconditional branch is the only potential thing we have. That leads us straight to the encoding page. And we can see that the one encoding that matches an unconditional branch is a branch with an immediate with 11 bits. And so we've actually hard-coded 11100 as the opcode. The rest of this is an immediate, and in this case, this is a sort of interesting immediate because it is a signed immediate value, because we can branch unconditionally forward to a label that's in the future, or we can branch backwards to something that's further up in the code, or further back in the code. And so we're going to take that as a signed immediate. We're going to convert it to the positive value by using 2's complement. So we're going to flip all the bits, add 1, and that tells us that this immediate 11 is actually negative 5. And so that's what we have there. That's not how branch instructions look, right? So B negative 5 is not what we would write in our code. That's not a thing that we do. Branch instructions are usually B and then a label name. And so that we look at the instructions then and see that assume that the only label in the assembly code is named loop, and so that must be B-loop. And that makes sense because loops often go backwards, right? We have a backwards edge that takes us, to where we started, and that's how a loop functions. So a negative 5 immediate would just mean that, we are going backwards 5 instructions, basically, or 5 addresses. Okay, so that's it for those. move on to the cycle counting problem. So in this case, we were looking to count the cycles in the assembly code. We'll take to execute. I do need to add to this that we assume taken branches cost 3 cycles and not taken cost 1 cycle, but that's the same as the homework. So hopefully that's understood. So here we're just looking these up in the ARM manual. This is reference D on the website, and seeing that moves are 1. Move W's are 1, move T's are 1, moves are 1. So this sort of prolog takes 5 cycles. Now we need to count the iterations of the loop. The loop, we can count each cycle and say that the load is 2. It's 2C, so that's one thing we'll use later, which is that a load or a store is 2 cycles unless we have anything sort of in the if we have the same address 2 instructions in a row. So if we don't have to do the address computation, we can immediately do the load or store. And so that would be 1 cycle if we had these 2 in a row, but we have something in the middle. The ALU gets used for something else, and so we lose that address computation. So it's 2 cycles, 1 cycle for an add, 2 cycles for a store, 1 for an add, 1 for an add, 1 for compare. And then a branch less than, a taken branch is going to cost 3 cycles. So when we do go back to the top of the loop, it takes us 3. A not taken branch is going to take 1 cycle to fall through to the next instruction. And that's because of that pipeline flush that has to happen. So we have to restart the pipeline when we mispredict a branch. We're going to assume that happens here. So now we have to do a little bit of understanding what the code does. Here we have that we set R1 to 0, we set R0 to 0. We're looking at the condition for the loop, which is we're comparing R1 against 10. Before that, we add 1 to R1, and then we branch less than to the top of the loop. So after the first iteration, we add 1, or as part of the first iteration, we add 1, and then we compare. And then we branch if it's less than 10. So it's 1 is less than 10, 2 is less than 10, 3 is less than 10, 4 is less than 10, 5 is less than 10, 6 is less than 10, 7, 8, 9 is less than 10. So we do 9 iterations where we branch less than. On the 10th iteration, we are going to not branch less than because we added 1 to R1. It's now 10. We compare against 10. That is not less than 10. And so we're going to exit on the 10th iteration. So that's what the math here is basically 0 to 9 loops, 10 exits. And so we have 5 cycles at the beginning, the prologue, plus 2 plus 1 plus 2 plus 1 plus 1 plus 1 plus 3 when we're taking the branch, when we're going back, that costs 3 cycles, times 9 iterations that we are going to loop. Plus, same thing, 2 plus 1 plus 2 plus 1 plus 1 plus 1, plus 1 cycle for the not taken branch when we don't loop, times the 1 iteration where we don't go back to the top. And so then that's 5 plus 99 plus 9 is 113 cycles. Give one optimization that can reduce the number of cycles in the loop. So there are potentially more answers here. I just gave 2 that are good ones here. So the first one is because this load R3, R2, and then the store R4, R2 doesn't depend on this instruction here. So the add R0, R3 doesn't change R4 at all. We could sort of condense the load and store together and do the load from R2 and then the store to R2 in 2 consecutive instructions, and that would save 1 cycle based on that rule in the ARM reference, which is that we have that 2C. So if we're going to the same address and the same size, we end up saving a cycle. So that would reduce the store to being 1 cycle instead of the load being 1 cycle. We could also actually, we couldn't reorder those because then that would potentially mess up the value we get from the load. But we can reorder these 2 instructions and do the store second, and that would save us 1 cycle. The other thing we could do is just eliminate R1. So we already have this memory address 10000000. We add 4 to it each time, and then we add 1 to R1. Well, we're doing these 2 adds here both times. We could instead, maybe put into R1 OX100040, and we could basically just use that value in R2 as our loop exit condition anyways. So we could, compare against OX100040, and then branch less than based on that comparison. and that would do the same thing as what our loop does currently, but now we don't have to do the 2 adds every cycle of the loop, and that would save us 1 cycle per loop iteration. So those are 2 things that are fairly simple that we could do. I mean, this is nonsense code anyways, so there are probably a lot of other ways to optimize it, but those are 2 reasonable ones to do. On to PWM. This is asking you to draw the resulting signal. So it's asking you to do the calculations, but then push it 1 step further and draw what the signal looks like. And you can see I made a mistake when I was working on it. I did the wrong calculation, or I wanted to change it to work with microseconds instead of milliseconds. So we do TMR0, which is the period, and that's going to be MR0 times PR plus 1 times TPCLK. So 10,000, just taking the values, plug and chug. PR plus 1 is going to be 1. And then PCLK is 100 megahertz. So 100 times 10 to the 6th cycles per second. And that gives us 0.1 millisecond, which is 100 microseconds. TMR1 is going to be the percentage, the duty cycle percentage, which is 40% here. So 4,000 divided by 10,000 times that 0.1 milliseconds, which gives us 40 microseconds instead. And so that's what we're looking at here. And that gives us then our chart is going to be at 3.3 volts, 1 volt. PWM signal looks like until MR1 it is high voltage, so 3.3 volts. At MR1 it drops to low volts, or 0 volts in our case, and it goes at that for the rest of the remainder of the period. So we're high for 40 microseconds, and then we're low for 60 microseconds. And then we repeat that signal, in perpetuity. Moving on to part B, we're looking at similar values. So we change the duty cycle percent a little bit. We increase the PR. So the prescale is what increases here, and then we decrease the clock cycle. So we should see larger timers here in general. So we do the same calculation, but now PR is 9, and TPCLK is going to be lower, so it's over 50 times 10 to the 6th, and we get 2 milliseconds out for our period. In this case, instead of using the cycle percentage to then calculate the time for TMR1, I did it just using the same equation but substituting in MR1, and that gives us 0.6 milliseconds. And so our period is 2 milliseconds. Our duty cycle time is 0.6 milliseconds, or 600 micro. And that gives us, again, we have the same 3.3 volts, 0 volts, and the same sort of shape to it as we had before. For part C, we're going to make the same calculations, but now we see that MR1 is actually higher than MR0. And like we've seen in the previous problems, when we hit MR1 is when we go to 0 volts. So if we hit MR0 first, the standard way that this works is that we're going to reset the timer every time we hit MR0. And that same timer is used for both MR0 and MR1. We don't have two separate timer counters. And so we're never going to get to MR1. We're always going to get to MR0 first. That means we're always going to be at 3.3 volts. So we never actually drop to 0. We don't really even need the timer here because it just always stays at the same value. So this is sort of a trick question, and you could do these calculations and then understand that because of the way that this generally works, we're never going to reset that timer, or we're never going to hit MR1, so we're never going to drop to 0 volts. Okay, on to the last problem, which is on digital conversion. This is sort of a design problem here. So you're designing an application that will detect changes in a person's singing ability based on the temperature and humidity in the air. Your application will play a pitch over the speaker and then record them singing that same pitch. So for part A, assume the highest pitch will be a B8 at approximately 7902 Hertz. What values should you set for clock div and pClock select to minimize the frequency of the analog to digital converter while still preventing aliasing? So we want to be higher than the Nyquist rate while minimizing the frequency that we're sampling at in general. So the Nyquist rate is that our sampling frequency has to be higher than 2f max. And so we take our f max, which is 7902 from the problem description, multiply that by 2, and that gives us that our sampling frequency has to be higher than 15804 Hertz. So our challenge is to find the best values for the PCLK and for the peripheral clock and for the clock div in order to get a correct value, or the closest possible value to the value that we want here. And I think I actually made a mistake here. We'll have to fix this in the notes, that this should be 1 less than what it is set to, because of clock div needing to be added by 1. But for now, let's just use what here. So we have 100 megahertz clock by default. We take 65 cycles per conversion, and those can happen at a minimum of 15804 hertz. So 65 cycles at 15804 hertz. We're dividing the clock by that value, and that gets us to, if we have a div of 97.346, that'll get us to exactly 15804. We actually want to set clock div to 96 here, because the clock div that gets used is going to be clock div plus 1, which would be 97. That's to prevent dividing by 0. So we're going to set this to 96, which will actually give us a divisor of 97. We can leave PCLK equals 100 megahertz because this divisor is already going to work for us. And that gives us a sample rate of 15,860 hertz, which is greater than the sampling frequency we need, but it's as close as we can possibly get without having fractional dividers here. Part B, would you use software controlled mode or burst mode to implement this application? So this is, you can justify burst mode probably as well. Depends on what you're looking for, but as long as you have a reasonable justification for this type of question, I will give you credit. I said software controlled mode because you're likely just going to, for something like this, you're going to check the temperature and humidity once or very infrequently. So software controlled works well for those because you can sort of do it as part of the application, when it starts up, and read those sensors basically, and record that value. Then otherwise, the sort of description is that you're going to play a pitch for them. You're going to let them sing it and then, detect or analyze how they sang maybe, and see how that changes their voice. So you're going to sort of play the pitch, listen to them, and then analyze it. So software controlled mode makes a lot of sense because you're sort of going to, play the sample for them over the DAC, listen for what they do, and then analyze what they did. And so it makes more sense to do that than have burst mode sort of converting the entire time and be like discarding samples in the background whenever you're not listening to them sing, right? And that also maybe decreases your chance of like having random samples that happened when they weren't actually singing, that had been recorded. For part C, so this is dealing with the bit rate of our conversions. This is something we talked about with regard to like CDs and DVDs, voice, all that sort of stuff that we covered in class, dealing with the sampling frequency and the number of bits we use per sample. So because it's hard to store a 12-bit sample into sort of 8-bit, 16-bit, 32-bit values, what we're assuming here is that we're going to use a short to store this 12 bits. So short is going to be 16 bits, or 2 bytes, but we're gonna sort of waste some space to be able to make it more simple to store. We could also look at this problem as, if we have 32 kilobytes, how many bits is that? And then, can we just store those 12-bit samples, and, maybe how much does that buy us to do that? But for now, let's just assume that we're using 2 bytes to store each thing. RAM on the LPC 1768 is 32 kilobytes, so that's from the the descriptions that we have. That's how much memory space we have. So we divide that 32 kilobytes, 32,768 bytes, by the 2 bytes per sample, and that gives us that we can store 16,384 samples in RAM. At a 20 kilohertz rate, we take 20,000 samples per second. So if we can store 16,384 samples and we take 20,000 per second, we have 0.8192 is our sort of percentage of a second that we can take a sample for, which is 819.2 milliseconds of recording time. So this assumes that nothing else is in memory, and that's how long we could record for. So it's a very small amount of time at that sample rate that we can record these for. So generally speaking, what we probably want to be able to do is maybe like analyze this in the background and figure out the frequency that they sang at, and sort of analyze them as it goes, rather than having to store all of these samples. So we might have a smaller buffer where we store a couple sine waves into, and then sort of analyze them, maybe do frequency extraction, power extraction, other techniques that we can use to then pass it into, for example, like a neural network or machine learning analyzer. But again, we have a very small amount of time that we can record for in this limited amount of memory. Okay, so on to part D. This one is looking at the number of samples that we would need and the ST reload values to play a C7 at 2093 Hertz out of the speaker. And it asks you to describe any issues with this number of sample. Assume the sample is attempt to replicate a sine wave, so it is, it is modeled after what we looked at in class, so it's as close as possible to a sine wave for that number of samples. Recall that the DAC can only be updated at 1 megahertz rate, so that's a warning that something will go wrong, that it is above that rate for one of these particular questions. So first, for 2 samples, we're using this calculation above, so we started off with the time is equal to ST reload plus 1 times samples over the CPU frequency, so that's the thing we've used in class. We are then working through that to find out that ST reload is equal to the CPU frequency over F times the number of samples, where F is the frequency of the note we want to play, minus 1, so this is just doing math, manipulating the equation to get what we need. So for the first one, if we have 2 samples, 100 megahertz is set. That's our CPU frequency. 2093 is set by the problem. That's the frequency we want to play. Times 2 samples is set by this subproblem. Minus 1 gives us an ST reload value of 23888. The issue with this is that 2 samples might produce a bad sounding tone because it's just low and high, right? So we wouldn't have a very nice looking sine wave, though if we're playing it fast enough, maybe it doesn't matter. But it's not going to produce a very good pure tone. 16 samples, so again, just plug and chug. 100 megahertz over 2093 hertz times 16 minus 1 gives us 2985. So no issues there. It's probably a reasonable sine wave because we have 16 samples in it. And then we have, the 2985 is a reasonable rate to update the DAC at. 2048 samples. Now we're going to have ST reload equals 100 mega over 2093 hertz times 2048 samples minus 1 gives us an ST reload value of 22. And the problem here, this is a little bit in the weeds, but we can only update the DAC at a 1 megahertz rate. At 100 megahertz divided by 22, we're actually going to be updating the DACR at roughly, a 4 megahertz rate. So 4 million times per second. This is faster than it can be updated. It's basically faster than the speaker can play something at, or that we can change this hardware at, because the DAC is, doing this sort of, resistor architecture. It doesn't update quite as fast as the rest of the circuits do. And so this will cause it to change faster than it can deal with, and we might get sort of partial wave playing here. So it's maybe going to miss some samples. It might downscale it so we miss every, we might only get every 4th part of this wave, which maybe is fine. But generally, this is just going to be too fast of updates to the DACR. It might just not allow us to do that and sort of, silently fail. But really, any ST reload lower than 100 will cause this issue, so we shouldn't try to use an ST reload value of this. It would be better in this case if we, reduce the number of samples to something more reasonable, so we have a faster ST reload or a slower ST reload value here. And so that's it. I know this was long. You can skip around to whatever you need to focus on here. But this is, again, to make the playing field level so that if you're not able to make it to the Group EI session on Thursday night, you still have this to fall back to with me explaining the questions. So good luck studying for the exam. I hope this helps.